Welcome to reactions of aromatic compounds. So we're going to talk about reactions in this particular section of benzene. And then I'll do another section where we do substituted benzene. So benzene undergoes EAS. You can think of it as easy, right? E stands for Electrophilic. A stands for aromatic. And the S stands for substitution. So in this reaction, we will substitute a hydrogen on benzene for an electrophile. And the mechanism for electrophilic aromatic substitution is going to be pretty much the same, and you will need to be able to draw this mechanism. First, you're going to have to, so step one, you will have to generate a strong electrophile, because benzene will not undergo electrophilic aromatic substitution without a strong electrophile. And then the next thing you'd have to do is you need to add it to the benzene ring to break up the aromaticity. So if we look at something like this, we take benzene, and we add an electrophile, then the first thing, this is your nucleophile, and those electrons will go and add to your electrophile. This will then break up the break up the aromaticity. So what happens here is this carbon will take on the electrophile, and this means the other carbon, so there's that bond there, the other carbon is going to have to get a carbocation. And these electrons are the same. So as you can see, this carbon here is now an sp3 carbon, because that carbon's bonded to four things, and the carbocation is an sp2 carbon. And so this is our, what we call a sigma complex. And this is high energy. It does not want to stay this way, because remember that aromatic compounds are more thermodynamically stable. And this can undergo resonance structures. So we can show this, where the electrons go there, and there's your positive here. And then we can generate another resonance structure. Remember our double-headed arrows. I should put my E there. Okay, so we have three resonance structures, and these are the sigma complex. Now, what happens then, you have some kind of negative base that will then take away the hydrogen for substitution. And so this will go after this hydrogen that's connected to the electrophile, and those electrons will move towards that carbocation. And then your product will be benzene that is substituted with whatever your electrophile is. Now, what we're going to be doing is we're going to show you different reactions that generate the different electrophile. Fungus now. So the reactions in this chapter that you're going to be responsible for are bromination of benzene, chlorination, if you want to make reaction sheets, nitration, sulfonation. We'll do Friedel-Crafts alkylation. And we'll do Friedel-Crafts, that's a name, acylation. And then we'll also show you how you can take alcohols and react them with Lewis acid to generate a carbocation, and that will be your strong electrophile that can then be added. I will also show you with Friedel-Crafts acylation another reaction called the Clemmensen Reduction, and that will not undergo E. So all of these will undergo electrophilic aromatic substitution, and we'll do these reactions with benzene, and this will also be your Pogel activity 20A. And then our next section, we'll talk about substituted benzene. And what I mean by substituted benzene, they're still aromatic, but something like toluene and different compounds like that. So that's 1, 2, 3, 4, 5, 6, 7, 8 reactions we're going to go through, and our Pogel on this section. So quickly, I will just go through one of these reactions here. So we know that benzene does not react with bromine. So it doesn't form the bromonium ion or anything like that. But if you add a Lewis acid, and remember Lewis acid, they accept electron pair. So a Lewis acid are lighter transition metals. Okay, so iron tribromide, and this has empty orbitals for the bromine to be able to put its electron pairs, and then you end up getting a complex such as this, where you have now made a positive bromine. And there's your strong electrophile. So the first step you always want to do is, in these reaction mechanisms, is generate your electrophile. And you don't have to show electron movement, but I do want to see that your bromonium, the bromium cation is your electrophile. So if you have this group here, I would like to see this. Okay. Now you can draw this. You can just pick one. I want you to put in both hydrogens for the 1 pi bond that you're going to show the mechanism with. So then you have these electrons going towards, from the nucleophile, the benzene ring, to your strong electrophile. And then I want to see your sigma complex. And you'll have to do this for your assessments. So one of those carbons here gets the electrophile, so you see the bromine, and the other carbon gets the carbocation, and this is your sigma complex. And if you were to draw resonance structures, you could draw this going here, double-headed arrow, put in your bromine, keep your hydrogen. Now you got the positive here, and then you can draw another. These electrons go here. Because technically in mechanisms you should draw all resonance structures. Okay. Now what happens, and you can pick any of these sigma complexes that have the positive charge right next to the carbon. I just picked the first one that you have, and here you could just show the negative iron if you wanted This should be Br3. Going to abstract. So you show your sigma complex. So 1, these are your steps. Generate your strong electrophile, or just put your electrophile up there. And then you need to draw electron flow arrows to generate your sigma complex. And then step 3, you need to abstract hydrogen to re-aromatize. So the next step is step 3, which is re-aromatization. And so the iron will come and take the hydrogen here, and those electrons will go towards the sigma complex carbocation, and then you can draw in your benzene ring. Now I would prefer you not to draw a circle. You can see that in your book, but for learning purposes it's good for your pi bond so you can show your resonance. And this is how you can do bromobenzene. And that's the mechanism. You're going to see this mechanism over and over. The energy diagram for this reaction. So you have energy increasing. And so we have benzene. So our starting material is benzene plus bromine and the iron tribromide, or you could say this is iron 3 bromide to be perfectly correct. And there's going to be a transition state. The valley is our sigma complex. That's why it's important for you to get this intermediate. And then the transition state 1. And then there's going to be another transition state 2. And then this is your product, the bromobenzene. And so the delta H would be here. And it's negative 45 kilojoules per mole. So this is an exothermic reaction. And that is the energy diagram for bromination. If you wanted to do chlorination, you would just use different reagents, Cl2, and you'd have to do like aluminum trichloride. And then together, that would generate the chlorine positive, and you could do aluminum tetrachloride negative. Also, if you wanted just to do iron trichloride, this also works. The next one, nitration of benzene. So your reagents for nitration is nitric acid. This is nitric acid. You should know that's one of your 7 strong acids. And you put this in sulfuric acid. So when you have HNO3 plus H2SO4, which one's your stronger acid? Okay. This one is good to be able to draw your Lewis structures. And your sulfuric acid. So which one's going to act as the acid and which one's going to act as the base? So this gets protonated. So this is acting as your base here, and this is acting as your acid. And then you get BOH, and you know that's a good leaving group. And then, of course, sulfuric acid. But we're trying to generate our electrophile. This leaves. This is your leaving group. And now you've got this, and this is your nitronium ion. And that's your strong electrophile. Okay? So if you see this together, you can just write NO2 positive. You don't have to generate this whole thing here. So if we do this reaction now, we have our benzene ring. You don't have to draw all your hydrogens, but you need to draw the one that's going to be abstracted. And you put this in HNO3 and sulfuric acid. That's going to generate the nitronium. And now you can draw your electron flow arrow. You want to draw your sigma complex. Put your NO2 there. Put your positive on the other carbon. That's your sigma complex. And then if you want, you can just say HSO4 minus is going to come and extract that hydrogen to do our re-aromatization reaction. And you reestablish your benzene ring, and now you have NO2. You don't even have to draw that. You can just, so this is nitrobenzene. So this is how you add nitro group to benzene. And it goes through the same mechanism. The Clemmensen reduction. So I said I would show you the Clemmensen reduction. So when you have nitrobenzene, something that's very helpful is you can do the Clemmensen reduction. And this is just a little bit of zinc, or you could put tin or iron in aqueous HCl. Usually you see like zinc, even mercury and HCl. You'll see just a different combination of these metals in acid and HCl, and that generates hydrogen gas that does a reduction. So this is a reduction, so sometimes we put H in brackets, and so we're going to reduce the nitro to an NH2. So this is called an aniline. You need to learn your vocabulary here. This is a nitrobenzene. And that is the best method for adding amino group to the amine. So that's how you can make an aniline. Okay, so the other reaction is sulfonation. Sulfonation of benzene. So these reagents are just sulfuric acid. It's called fuming sulfuric acid. So that is sulfuric acid with 7% mixture of SO3, which is sulfur trioxide, and that is your electrophile. Remember, sulfur can do an expanded octet. And so when you see these two reagents together, there's no water, it's just the SO3. And so now when you have benzene, you write your SO3, and now you can draw your mechanism here. And you're going to get your sigma complex. This is going to go SO3, and then it's going to pick up an H. Okay, so it's going to pick up an H from the sulfuric acid. So you can just go ahead and do that, and then you can put your positive. So you can write sigma complex. And then you can show the HSO4 minus doing the re-aromatization here. So it takes that hydrogen, that electrons go back towards the sigma complex, and SO3H. And this is SO3H is considered a sulfonic acid group. That's sulfonation of benzene. So in each of these, you want to generate your strong electrophile. The other reaction is nitration of toluene. So, and we'll talk about nitration of toluene in your next section. So these are substituted. Let's go to the Friedel-Crafts, alkylation, acylation, and then we can work our PG20A. Okay, so Friedel-Crafts alkylation, and this is a way to make a carbon-carbon bond. So if we have something like, let's say, methyl bromide, and so it can be the alkyl bromide, it could be an alkyl chloride, it could also be an alkyl iodide. So any of these would work. You could also do something like this with an ethyl group. Now, you have to put in a Lewis acid to generate a strong electrophile. So you can use like aluminum you'd want aluminum tribromide if you're going to use the alkyl bromide. Or you could use iron bromide. One thing I used to use, like titanium, actually tetrachloride. But anyway, but you want the halogen to match. So what happens here is when these come together, these metals have a strong affinity for the halogen. So those electrons will go with the Lewis acid, and then essentially what you've generated is a carbocation. So this is what you've generated, and that's how you see that you have your strong electrophile. And now we have our benzene. Those electrons go here. We form our sigma complex. So we have our CH3 there, and our sigma complex here. Sigma complex. And then we need to re-aromatize. So you can just do the aluminum tetrabromide. Those electrons will take this hydrogen. Those electrons go towards the sigma complex. And that is how we make, in this case, that's toluene. So kind of go through your slides and understand how to name these. So that makes toluene. You could also make carbocations by protonation with HF. So you can generate an electrophile this way. Now you have the hydrogen goes here, the carbocation goes here, and then that carbocation could add to benzene. I will just draw the product here instead of going through the mechanism for time. So we have 1, 2, 3 carbons. 1, 2, 3 carbons. If you have an alcohol, so here we have a secondary alcohol, you can use something like BF3. BF3 is a great Lewis acid, and that means those electrons on the oxygen will go into the boron. So what does that structure look like? We have it's sp2 hybridized, so there's this unhybridized p orbital that those electrons can go and coordinate with oxygen. And then what happens in this essentially an acid-base chemistry reaction is the electrons here will go towards oxygen. And so boron is going to form a very tight bond with oxygen. So it's not going to let that go. And now you got a carbocation. And then that carbocation can add to benzene. And I wonder how really good this reaction would be. I am a skeptic here, but there you go. Could probably work really well. All right, so you have to be careful with Friedel-Crafts alkylation because whenever you're generating a carbocation, if you remember from SN1 and E1, you get rearrangements. So whenever you do that, you need to do what I call the carbocation stability test. So, an example, what if you had this, okay, and you say, well, okay, I'm going to get this. I'm going to tell you you're not going to get that, okay, because what's going to happen is you're going to generate your carbocation. Okay, so there's your strong electrophile. But you do your carbocation test. That's a primary carbocation. Next door, you did a hydride, a 1,2 hydride shift. Now you have a secondary carbocation. You know that's more thermodynamically stable, and so when this adds, then you get, your product is going to be isopropyl benzene. Okay, so how would you make this? So how would you make this compound? How would you make that? Well, you could use a Friedel-Crafts acylation followed by a Clemmensen reduction. Okay, so see the word acylation. So in this case, take benzene and you react it with an acyl chloride. So this is 1 carbon, 2 carbon, 3 carbon. So this is called an acyl chloride. It is also an acid chloride. Okay, so it's an acid chloride functional group. Now you can react this with a little bit of aluminum trichloride. So you want to add a Lewis acid. And together, this is going to make this electrophile. Okay, so you're going to generate, this is called the acylium ion. That's your strong electrophile. And then you're also going to generate aluminum Cl4 minus. And so what happens now is this can add here, make our nice little sigma complex. Put the hydrogen in there, hydrogen there. There's our sigma complex. And then aluminum tetrachloride could come in here, take this hydrogen away, and re-aromatize. 1, 2, 3. Always count your carbons if you want the right answer. Now, Clemmensen reduction. Zinc. You remember Clemmensen to make anilines? Zinc, a little bit of mercury, and HCl. And that's also going to reduce, so it will remove the carbonyl. So it'll replace carbonyl with a CH2. And that would be how you could make the N-propyl benzene. The N just means it's not substituted. I think I was in graduate school before I actually knew what the N was. So that is essentially all the reactions we're going to be responsible for PG20A. So let's look at PG20A models. So we have PG20A. Okay, we have this potential energy. And so this is our reaction energy diagram. We have reaction 1, and it goes here and here and here. And then we show our anti-addition of bromine. And then we come down here and we have benzene, which benzene is more stable because it's aromatic. And then it goes up, and we have this compound with the bromine going anti. And then we make sure we have that there. Now, this is reaction 2. And this is the reaction progress. And these are the reactions. If you were just to look at them, plus bromine, that's reaction 1, and then reaction 2. And it's showing you here that it doesn't work. It's not happening. It's not going to happen. And that's reaction 2. All right, so 1A. The starting alkene is what for reaction 1? Isolated. Yeah, it's an isolated alkene. The energy diagram for reaction 1 shows that the reaction is, okay, so if we take this energy here and this energy here, it's going to be exothermic. Question number 2. Okay, the starting alkene for reaction 2 is deuterate conjugated. So this would be conjugated. It's actually aromatic. Energy diagram for reaction 2 shows that the reaction is, so we did the energy difference here. Did you come up with exothermic? Exothermic. Which alkene is lower in starting, is lower in energy? The benzene. So this would be lower in energy. Which reaction has the higher activation energy? And so if you did the activation energy, it's from here to there. Whereas from here, it's here. So reaction 2 would have the higher activation energy. Reaction 2 does not occur. In your group, discuss why the reaction of benzene is unlikely compared to reaction 1. And you can write the activation energy is too high. And the reaction is endothermic. So it's not going to happen. And that's what we've been talking about. So now we have to use a different mechanism, and it's called electrophilic aromatic substitution. We'll talk about that in Model 2. So Model 2 is electrophilic aromatic substitution. Ease. And let's look at this model. We have benzene. Notice that the hydrogens are drawn, and we're showing you the electrophile. And we're saying this is a very slow step. And those electrons are going to add to the electrophile to make a sigma complex. Okay, so let's draw our sigma complex. The electrophile has added. This is sigma complex, also called the Nitrionium ion. And you put that in brackets, and then some form of base will come and take this hydrogen. Those electrons go there to form the rearomatization. So let's answer 4A. So this is the general reaction of benzene reacting with an electrophile. Benzene is conjugated, not isolated. What is the role of benzene in the first step? It's acting as a nucleophile, right? Explain why the first step is the slow step. Well, that means the activation energy is high. And it will be. You're breaking up an aromatic system. You're making this carbon right here an sp3 carbon. So that is going to be a high activation energy. 5A. What is the charge of the sigma complex? You see that positive? Sigma complex is positive. Draw all resonance contributors for the sigma complex. So this is always good practice. You want to show those electrons move here, double-headed arrow, redraw. And then we can draw another one, double-headed arrow. Okay. In the second step, the base abstracts a proton. So this base is abstracting this proton to form the substitution product. What is the role of the sigma complex? Now the sigma complex is your electrophile. Or, I think it's better just to write acid, right? Because it's going, so acid would be good. As a group, discuss whether the second step would occur readily with a weak base. Absolutely yes, a weak base. And that's because rearomatization is a strong driving force. So when you're doing this, it's a very strong thermodynamic driving force. And sometimes you would say that's like a downhill energetic activity. Okay, and then number 6. Draw curved arrows to show the electron movement for the reaction in Model 2. So let's do this. So the first thing you have is your electrophile. You want to show those electrons adding. This is your slow step. And you show your sigma complex. I'm going to draw mine like this. Here's my sigma complex. And you should be able to draw this mechanism. Now the base is going to come in and take this hydrogen, those electrons go there to do the re-aromatization. And now you have your electrophile added. We really don't care about the BH. Let's do Model 3. Model 3 has all the reactions you're required to know. So Model 3, let's get all those reactions and we can answer the questions. These are electrophiles and electrophilic aromatic substitution reaction. And so your nucleophile in all of these are benzene. And your electrophile, it's nice, it kind of tells you what your electrophile is. Here we have Br+, Cl+. This is what I expect you to be able to do. This one you have NO2+. This one is SO3. This one is an R+, which is your carbon cation. And then this one is an acylium ion. And then what's really nice here is the reagents are listed to generate. So this one, you could even put bromine with iron 3 bromide, or you could use chlorine, aluminum trichloride. With the nitro group, you need nitric acid and sulfuric acid. With the sulfur trioxide, you need about 7% sulfur trioxide and sulfuric acid. And for this is your Friedel-Crafts alkylation. So you just need some kind of leaving group. X is your halogen, and you need a Lewis acid. And then this one here, you have an acid chloride. So you have acid chloride, and then you also need like aluminum trichloride because you need a strong Lewis acid for that. Now, what's your product? So sometimes you don't have to go through the whole sigma complex unless it asks for the mechanism. Now on your POGIL exercises, I do want to see the mechanism because you're learning for the first time. So this time X is either chlorine or bromine, and this is called halogenation. The next one, you add nitro to the ring, and this is called nitration. This product, you add SO3H. Okay, that's called sulfonation. This one, you're adding the R group, and this is called Friedel-Crafts acylation, alkylation. And this one, you're adding an acyl group, and this is called Friedel-Crafts acylation. So those are the reactions you're responsible for. Now let's answer the questions. 7. All E's reactions occur by the same general mechanism as outlined in Model 2. The only difference lies in the formation of the activated electrophiles. So here we have the activated electrophiles. Consider halogenation the first entry. For bromination, what is the actual electrophile? Did you put Br+? What are the reagents used to generate the electrophile? Did you write bromine and iron 3 bromide? What is the electrophile and reagents for chlorination? You write Cl+, and then the reagents here. For halogenation to occur, this is halogenation, a Lewis acid must be used as one of the reagents. What is the general definition of a Lewis acid? Well, a Lewis acid accepts electrons. A pair of electrons. In the list of reagents for halogenation, what are the Lewis acids used? Aluminum trichloride and iron 3-bromide. Okay, question number 8. When bromine reacts with iron 3-bromide, an activated bromine complex is formed, shown below. Draw curved arrows to show the electron movement from forming this activated complex. And I'm not going to require you to do this. I just want you to be able to write what your strong electrophile is. But it's basically the electrons go to the bromine just like that, and you get, I like to actually put, well, this is what it's supposed to be, because the iron gets a negative charge. The activated bromine complex is a strong electrophile. This is a strong electrophile and can react with the benzene as outlined in Model 2. As a group, determine which bromine in the activated complex would accept. So it would be this bromine here. Draw curved arrows to show electron movement in the first step of the ease. Put a plus charge on the correct position. Okay. So if we did this, and I'll just go ahead and put the plus there. So at this point we have this hydrogen that you want to draw in, and you can draw this hydrogen as well. Those electrons, I would just go after this one here. And so you see that you make the negative iron 4-bromide here, and then you have the bromine adding, and you have the sigma complex, that's important, and then these electrons will do the re-aromatization, and that's what this question is asking you for. And you have that hydrogen's there, and that bromine is there. Okay, in the final step of E's mechanism, this is 8D, base removes a proton from the sigma complex to give the substitution product. Draw curved arrows to show this movement. So we've been doing this. So here we have the hydrogen, and we have the bromine, and we have the iron bromide 4, and then you would just show the electrons taking this hydrogen and those electrons going towards the positive carbon. And that is your product. Draw curved arrows to show which proton is eliminated and to show electron movement forming the final products. Which species acts as the weak base? So this will act as your weak base, the iron 4-bromide. Okay, number 9. Consider the nitration reaction. So number 9, we're doing the nitration. So you can go and look back on your model for number 9. The nitronium ion is formed in the reaction of nitric acid and sulfuric acid. And I showed this earlier. So you should be able to see that. Which species acts as the acid? We talked about sulfuric acid is protonates the nitric acid. So and here we get protonation, and then this makes a good leading group, and that's how you get the nitronium electrophile. Does oxygen, so this is your acid, does the oxygen in the water that is eliminated come from, where does it come from? It comes from the nitric acid. So there's your water. Show how an alcohol is protonated with strong acid. Compare this to the protonation of nitric acid by drawing curved arrows to show the formation of the nitronium ion. So here we have alcohol, and you have sulfuric acid, and the alcohol gets protonated, and that gives you the ROH, which makes it a good leaving group. That's what you want to draw in there, and then you have this goes to water, and then we have the nitronium. And here you have sulfuric acid, so if you do the same thing here, it gets protonated. And then the species you have here is protonated water, and that goes on to form the nitronium. Question number 10. Use of a carbon electrophile in the E's reaction is called the Friedel-Crafts reaction. So now we're doing a carbon electrophile. The alkyl chloride is activated by reacting aluminum trichloride as shown below. Draw curved arrows to show electron movement in the reaction below. Put charges on the intermediate complex. So what happens here is these electrons from the chlorine go to the Lewis acid. This forms a carbocation. And you can see your intermediate there shows something like this. And those electrons will go. Draw the product and the complete mechanism for the reaction of benzene with the cation above. Make sure to draw all resonance forms of the sigma complex formed. All right, so let's draw this mechanism with this Friedel-Crafts reaction. So you draw your benzene. Let's draw in our hydrogen, so we're going to show our complex. Like I said, I just want you to show me your strong electrophile and your mechanism. Here's your carbocation. Now you can show those electrons going there to form your sigma complex. We also have our hydrogen here. We have a positive there, and then we have our bonds there. So this is our sigma complex. And then you can show the aluminum tetrachloride coming in and taking this hydrogen to do the rearomatization. And then you can show your product here. And let's just do the line drawing. So there we have. And that would be your butyl benzene. Oh, it says all resonance structures. So what would your resonance structures be here? So if you had this, you could have this. You could also have this here. So you have 3 resonance structures. That's good practice. All right, the next page, the question C. Secondary and tertiary alkyl halides form the cation prior to the reaction with the benzene. As a group, discuss whether primary alkyl halides would form the cation. So they're asking about something like this. Okay, and would this form? So if you use aluminum trichloride, could you form a primary carbocation? And no, because it would rearrange. So you would end up forming this secondary carbocation. Anytime a cation is formed, rearrangements can occur if a more stable cation is produced. Circle the alkyl halides that would undergo rearrangement in a Friedel-Crafts alkylation reaction. So now you want to see which ones would undergo rearrangement. So here you have the propyl. So if you made your carbocation, you did your carbocation test, that one would definitely show rearrangements, right? What about the allylic? So what would that look like? And then you could get a resonance structure here, but that one would be okay. Okay. Here, what would that be? And then you would get the hydride shift. And so that would show rearrangements. What about this one? You form your carbocation. That one would be okay. So you can do your carbocation test. Draw the major organic product for the following reaction. How many carbons is that? 4. So butyl chloride with benzene. You put in aluminum trichloride. And then what I want to see is you go ahead and generate your carbocation. So you want to do this. And then I want to see the rearrangement. So here you have the hydride shift. 1, 2, hydride shift. And that would give you this carbocation. And then that is what's actually going to add to your benzene. And so the product you would actually get would be this compound. What is the name of this compound? That would be sec-butyl bromide, sec-butyl benzene. So you would actually get sec-butyl benzene. Friedel-Crafts acylation involves a carbonyl electrophile. Okay, so question number 11. We're talking about Friedel-Crafts acylation. Not alkylation, but acylation. It involves a carbonyl electrophile. What does that look like? That looks like this. This is a carbonyl. And occurs similar to alkylation to form the cation shown. So here we have an acid chloride. And we react this with aluminum trichloride. Those electrons go onto the aluminum to form AlCl4. And then you get your acyl carbocation. Draw curved arrows to show electron movement. And so the intermediate that you have on your POGL exercise looks similar to this. And so you could do positive here, positive, negative. And the intermediate cation in Friedel-Crafts acylation does not undergo rearrangement. In your group, discuss reasons why rearrangements would not occur. So let's look at this. This is more stable of a carbocation. What would its resonance structures look like? So let's draw a resonance structure for this. You do a triple bond. 1, 2, 3, 4, 5, 6, 7, 8, and then oxygen would have a positive charge. So this has a resonance structure that is stabilized. Now you have additional exercises 12. It says draw the product of the reaction of benzene with each following reagents. I want you to draw out benzene, and I want you to draw your two hydrogens. I want to see your mechanism. So I want to see the sigma complex. And for like sulfuric acid and nitric acid, all you have to do is show the nitronium. So I do want to see the NO2 plus in your mechanism. Same thing with B, C, D, and E. I want to see what your strong electrophile is in your step 1. Form your sigma complex. I need to see electron flow arrows and your product. 13, explain why Friedel-Crafts acylation cannot be used. You can use words, but I want to see that reaction. I want to see exactly what happens and what that reaction product would be. And that should complete your additional exercises for 20A.